Right. Morning, everybody. How you guys doing today? So today, all we're going to do is go over the homework, talk about the review, get ready for the test tomorrow, and that's it. And let me see if I can find us here on the chat room. I got to open that up so I can see you guys. So just say hi if you're there. And little heads up about the test tomorrow. It's going to be a short test. It's not going to be super long or anything. It's going to be pretty short, shorter than the last one, but it will count as a test. Okay, so just keep that in mind. And it's going to be just on basically the stuff that we've learned. Okay, so make sure you're able to do like your pH calculations, write out your acid-base neutralization reactions. Make sure that you can identify different types of acids and bases. Figure out what's your acid, what's your base, what's your conjugate acid, what's your conjugate base. Make sure you're able to figure all that stuff out. And it will be just as always, it will be open notes. So you guys are welcome to look back at that. And just like always, you may not talk to anybody about it. You may not share your answers. You may not share any kind of that kind of stuff with other people or discuss your answers at all. Okay? All right. So, all right, I'm looking at the chat here. Sam says, I wrote down 2 questions to ask you, by the way. So when are you ready for, okay, I am ready for questions right now. And yes, I remember you. Hi, Max. All right, so whenever you got your questions, you can start with your questions, and then we can go ahead and jump into solving these problems. Could you explain the buffer formula? I actually don't want to get into the details of the buffer formula. I can explain what I want you guys to know, and that's about it, okay? Because buffers can be a fairly complex concept, but I just want to make it as simple as possible, all right? So what do you need to know about buffers? First of all, they resist change in pH. So if I add acid or base, the pH doesn't change very much, okay? And they simply are a weak acid and its conjugate base, or a weak base and its conjugate acid, and technically speaking, those are the same thing, no matter how you slice it. Okay, so we're going to go through, probably the most important thing for buffers would be something like number 6. We're going to go through number 6. I actually really quickly went through it at the end of class last time, but I want to go through it in more detail and think about that. All right, so also numbers 4 and 5 would be important, but 4 and 5 are really, really straightforward, okay? So how would you make a buffer from a weak acid? You add its conjugate base, or you partially neutralize it, okay? And then same thing here. Let's just jump down and do number 5, okay? We'll jump down and do number 5 right now. Ammonia is a weak base. How could you make a buffer from it? Well, if it's a weak base, we could most easily add its conjugate acid. So we're going to add NH4+. All right, so what would that be? That might be adding, let's say, ammonium chloride, or ammonium, bromide, or whatever, ammonium sulfates. That would be a little bit more complex, but the same idea, okay? So we're going to add some of that to it. Ideally, you would want to have a 1-to-1 ratio, but it's not necessary, okay? Secondarily, you could partially neutralize. Partially neutralize it. And partially neutralizing it so that you might have, let's say, 1 mole of your ammonia solution, NH3, and we're going to add, let's say, 0.5 moles of HCl. Now, you could add other acids. I just find HCl is kind of your go-to simple basic acid, strong acid. And so when I have half of this neutralized, it's going to turn half of this 1 mole of ammonia into NH4+. So either way, you're going to have a buffer solution. All right, so looking at some more questions here. I kind of think I got number 10 right on 9.4, but you're confused about it. All right, we'll look at number 10. We'll go through the whole backside. Before I go through the backside, I want to do the front side. All right, but we'll address that. And then, okay, could you go over number 13 on 9.2, but could you do it with an acid like HBr instead of base? Ooh, let me see if I could find that. Number 13 on 9.2. I got to look through my previous stuff. 9.2. Okay. Oh, that, you know what? I'm going to say, make a solution of, you know what I'm going to say for number 13? That's a good question, and that's so that's a hard problem we went through way back 2 homeworks ago. So Sam, when we did this problem, that was kind of our reach type problem, our extend type problem. I promise you, you will have nothing like that on the test, okay? So I don't want to take the time right now to go over number 13 or a similar one like number 13, only doing it for, you know, the acid type form. I just want to say, okay, that was a reach problem, so you could kind of try something difficult out on the homework, but I'm not going to put that on the test. Promise you, nothing like that on the test, because this kind of requires that you understand bases, or sorry, you understand logs a little bit more than maybe you do. Okay, and so if you guys are really good at logs, this shouldn't be too bad. But I think it's a new concept for you guys, so I don't want to give you guys that. All right, I'm having a little bit of a lag problem, so I'm going to have to refresh this. Anyway, all right. So that said, I'm not going to go over that one just because it's not going to be on the test. And I want to focus on that stuff. But let's see. What other questions? Cloud, explain how to determine what compound do we need to add to form a buffer. Okay. So back over here with the buffer stuff. You don't need to necessarily say sodium acetate or ammonium chloride. You just need to say that you add NH4 plus or you add your C2H3O2 minus, okay? That's the key part that you guys need to be able to know. And all you need to do is, if you know is NH3, you need to know, okay, what is the conjugate acid? If you know that this is a weak acid, you need to be able to figure out how, what is the conjugate base to that, okay? And so that's basically going up to number 3 right up there. You have to be able to figure out the conjugate acid or the conjugate base of something. All right, and you have to realize, okay, if this is a weak acid, you have to add the conjugate base, not the conjugate acid to it. So if you said add H2C2H3O2 plus to it, that's not really the right answer. Okay, that would not be a buffer. Okay, so you have to be adding the conjugate base to a weak acid or adding the conjugate acid to a weak base, and that's it. This other stuff, you don't specifically need to know sodium or chloride or anything like that. The second one. Let's see. Hold up. Let me just go through these questions here. Could you do the last one on number 3 too? Yeah. All right. So what I'm going to do is, I'm getting a lot of questions that are taking me all over the place. What I'm going to do is I'm just going to go through all these and then answer more questions you guys might have. Okay? And so if we need to go back to a previous homework, we will, all right? But I'm just going to go through these and make sure you guys are understanding these. If you guys get stuck along the way, we'll stop at the end of page 1 and we can answer any of those questions. The second page is just review. Okay. So back up here to the whole idea of conjugate acids and conjugate bases. We've seen them in reactions, and you have been identifying them in reactions, but what if you just have the chemical itself? You should be able to, figure out what it is. And it's really simple. To do a conjugate acid, all you're going to do is simply add H plus. That means you're literally adding an H to the formula, and the charge is going to increase by 1. Okay? So if it's neutral, it's going to be +1. If it's positive, already, it's going to be +2. If it's negative, then it's going to be neutral. So you're adding an H and a charge, right? For the conjugate base, we're doing exactly the opposite, right? We are going to remove one H plus. Okay, so we've already done a couple of these examples. Let's go ahead and do some more, and I can just split this up. You guys should have already done this for homework. So the conjugate acid of H2SO4 is going to be adding an H plus, so that's going to be H3SO4 plus. All right. The conjugate acid of HSO4 minus is going to be, well, adding an H plus, that turns into H2SO4. All right. The negative charge goes away because we've just added H plus to it. The conjugate acid of carbonate is going to be HCO3 minus. And notice that the -2 charge is turned into a -1 charge. That's what happens. And notice this is now a little bit of review for you guys. You guys learned about carbonate and hydrogen carbonate, and now we kind of see, okay, well, how they are related to each other. Why, hydrogen carbonate has a 1- charge rather than a 2- charge. All right. What about the conjugate bases? Conjugate bases, you're just going to remove an H plus. So we've already done that for water and ammonia. How about sulfuric acid? Sulfuric acid, when it loses one H, is going to be HSO4 minus. Okay? And the conjugate base of that, so when you have HSO4 minus, the conjugate base of that is going to be SO4 2 minus. So we're taking away another H plus, and the negative charge is going to become negative by 1 more. Now, when you come down to the very, very last one, and you say, okay, the conjugate base of carbonate, well, what do you do with that? How do you remove an H plus from that? And you can't, because it doesn't have any H's. So we're just going to say there is none. Okay? There is no conjugate base of carbonate. And in fact, we can say carbonate can never, ever, ever act as an acid. Okay? So it's not amphoteric. Actually, a lot of things, everything here that I've listed is amphoteric. Remember, amphoteric means it can act as an acid or a base. But carbonate is not. It can only act as a base. It cannot act as an acid. It's not amphoteric. All right, the rest of these guys are all amphoteric. So we've gone through number 4 and 5. When you want to make a buffer, you simply add the conjugate base of a weak acid or add the conjugate acid of a weak base, or you partially neutralize it. Which brings us down to number 6, analyzing something. All right, so a couple questions before I answer number 6. So how did you know the conjugate base of H2SO4 had a positive charge? So because you have to, well, you're removing a positive, let me see, which one was it? How do you know the conjugate base of H2SO4? All right, so H2SO4 has no charge. If I remove a positive 1 charge from it, it must turn into a negative charge, right? So you just subtract. So for all of the conjugate bases, the charge is going to be -1. All of the conjugate acids, the charge is going to be +1 of whatever it is, okay? So that's why, so HF is neutral, so this is positive and this is negative. H2 is neutral, so this is positive, this is negative. Same thing, neutral, which means this is positive, this is negative. Neutral, this is positive, this is negative. Now this is negative, so when you add 1, so this becomes neutral, and this becomes -2, okay? So the conjugate acid is always going to be +1 for the charge, and the conjugate base is always going to be -1 for the charge. All right. So lots of comments here. Not all of them are questions. All right. How did you know the conjugate base? Okay, I think I answered that one too. All right. When it doesn't, yeah. Uncultured. Okay. All right. So if I missed a question, sorry. You can come back and ask it again. All right. But simply put, you need to pay attention to what's going on here. Okay. You're going to be adding an H plus or removing an H plus, and that's not just an H. That's an H, and it's a positive charge. That's an H and a positive charge. So the conjugate base is always -1 for the charge. Conjugate acid is always +1 for the charge. All right, down to number 6. Number 6, let's think about these and see, okay, which one's a buffer, which one's not. And I think we already have discussed this very, very quickly last time, but I want to look at it a little bit closer because I can tell you're going to get a question like that on the test. And so this is definitely going to be, you know, one of your test questions. This is not going to be the focus. The focus is going to be the stuff that we've done already. But that said, very simply, you need to identify, okay, what's a buffer, what's not. But don't worry, I will tell you whether something is a strong acid or a weak acid. That's information I give you, okay? So that you don't have to worry about. So as soon as you see in number 1, I'm sorry, in letter A, as soon as you see HCl, oh, Mr. Kett said HCl is a strong acid. As soon as you see that, you're thinking this is not a buffer, unless the other thing over here is a weak base and you're somehow neutralizing it, but you're, partially neutralizing it, but you're not, okay? So, that's not the case. NaCl is just a neutral compound and we're taking a strong acid. So this is a strong acid and its conjugate base. A strong acid and its conjugate base is not going to be a buffer. So not a buffer. And the reason is because it's a strong acid. And strong acids and strong bases are not going to be buffers. Okay. B, we have HF. And I said HF is a weak acid. So as soon as you see that's a weak acid, and what is this? What's sodium fluoride? So that's HF and F minus. Remember, HF, its conjugate base is F minus. So weak acid and conjugate base. Weak acid and conjugate base, that's going to be a buffer. And it's going to be a buffer regardless of the amounts you have. So whether it's 0.5 and 0.5, 1 and 1, 1 and 2, let's say 3 and 1, whatever the ratios are, doesn't matter. You have a weak acid and its conjugate base. Doesn't matter whether this is sodium, potassium, lithium, whatever is over here, that's going to be a buffer. It's because you have a weak acid and its conjugate base. Next one. Once again, we see a weak acid, HF, but you're reacting it with a base. Now this one, pay attention what's going on. If you react a weak acid and a strong base, so sodium hydroxide, and it says up here, NaOH is a strong base, what happens is you are going to neutralize that. And now it's important the amounts, okay? Because partially neutralizing a weak acid will create a buffer, but fully neutralizing it will not. It'll simply just be a neutralized solution. So you have 0.5 moles of that and 0.5 moles of that. That's a 1-to-1 ratio. And so that is going to be completely neutralized. And you don't need to really worry about the neutralization reaction here. We could go through it, but it's not important because you know that you have an equal amounts of acid and a strong base, so you're going to completely neutralize it, so it's not a buffer. Okay? And so here we have in D, you have, once again, the same weak acid, and now you have, once again, a strong base. But the key here, the key difference, is you have half the amount of base. So weak acid and half the amount of a strong base, that's going to be partially neutralized. And when you partially neutralize something, when you partially neutralize a weak acid or a weak base, that's going to be a buffer. Okay? Partially neutralization, buffer. Last one here, we've got sodium chloride and sodium fluoride. Well, that's nothing that we've talked about, right? That's a salt. That's a salt. That's not going to be anything. That's not going to be a buffer. You can think of it this way. So this chloride is the conjugate base of a strong acid. That's nothing. Sodium fluoride is the conjugate base of a weak acid, but it doesn't matter. It doesn't, you're mixing two salts together. That's nothing. That's not a buffer. Right? So the key features that you're going to be looking for is a weak acid, okay? In each of these cases, you have a weak acid. And here, you're adding the conjugate base, and here you're partially neutralizing it, okay? And so for B, it doesn't matter what the amounts are, right? As long as you have the weak acid and its conjugate base. But here it matters the amounts. If you had a strong base, some other base, a strong base, you have to have a partial neutralization, not a full neutralization. Okay, so lots of comments, so I'm going to look at these. And right now, guys, right now is a good time to ask me a question if you want to ask a question about the whole buffer situation, but I think that's about it. Probably numbers 3 and 6 being the most important. So 3 and 6 being the most important on this front side here. All right. So, cool. What happened to the sodium? What happened to which sodium? You mean, oh, here, down in 6B, nothing happened to it. The sodium's there. The sodium's just not important. That's why I didn't write it over here. And so you could have sodium fluoride, you could have potassium fluoride, you could have any kind of fluoride. You just need to recognize, okay, that the fluoride is the conjugate base of this HF, okay? And so as long as you recognize, okay, this is an acid and its conjugate base, then you're good to go. Then it's a buffer, okay? So the sodium, it just isn't important, but you have to have something there, right, whatever it is. So don't, and that's probably the trickiest part. Honestly, that's probably the trickiest part of number 6, is just looking through the other non-important information, like the sodium, okay? Just ignore those. They're called spectator ions. They're ions that don't really do anything. All right. So other questions. How can you determine the NAF is a conjugate base? Simply, how can you determine it? Simply because you look at HF and you take away H+. So you should be able to do that. That's very important. You look at the HF and you say, okay, what's the conjugate base of this? Because this is a weak acid, the conjugate base, take away H+, and it turns into F-. And you just say, okay, you ask yourself, does this contain this? Regardless of what this other sodium is. You say, does this contain this? And you say, yes, sodium fluoride does contain fluoride. All right, and that's what you're doing. The process of this is HF, first of all, that's a weak acid. What's the conjugate base of it? The conjugate base of it is F-. Does this contain F-? Yes, therefore it's a buffer. That's the thought process. Okay, are we going to go over a review? You have a review guide. Guess what? It's the second page of this homework. And we are going to go over it right now. All right, you should have done it already, but we're going to go over it right now. Now, the review guide doesn't have any review of this. Again, because this is not going to be the focus. You will have like one buffer question, and you'll definitely have a conjugate acid, conjugate base question, but that's it. Okay? So let's go ahead and, rather than spend another 20 minutes on buffers, let's go ahead and go on to the review. Thank you, Braden, for asking. Let's do that. So let's not miss the easy questions when we focus on the hard questions. That would be a problem, right? So let's go ahead and do that now. Let's start up at the top and go through all of these. We need to be able to go through Arrhenius acids and bases, Bronsted-Lowry acids and bases, and there will be one question on a Lewis acid base question. All right, so make sure you know all those. I know I had a question on number 10. Somebody's like, what in the world's going on there? That's because Lewis acids and bases don't need to have any H's in them. So without further ado, let's start with number 7, and I'm going to go through all these, and stop me if you want me to say more on a particular problem. All right, so number 7, classify each of these as acids and bases. We've done a question like this in a previous homework. So for Arrhenius, pay attention to the wording of the problem. For Arrhenius, you're just going to be looking for an H in front or an OH minus in back, and keep in mind that things like water, so as soon as you, so pick out strange things. So things like water are neutral, although it looks like, and so neutral, what I mean by that is going to be neither. It's neither an acid nor a base, according to Arrhenius' definition, right? Obviously, water, according to the Bronsted-Lowry definition, can be both an acid or a base, depending on the situation. But for the Arrhenius definition, water is not going to change the pH. It's not going to make it, increase the amount of H plus or H minus, right? That's the solvent. So H2O is neutral. It's the only thing that's neither an acid nor a base that is H in front, okay? Otherwise, we're looking for H's in front. Anything that's an H in front is going to be, all right, let's go ahead and use this. It's going to be an acid if it has an H in front. H in front, that's going to be an acid. H in front there, that's going to be an acid. Okay? No H in front, no H in front. Neither of those is an acid. Is either one a base? Yes. Rubidium hydroxide is a base. Why? Because it's a hydroxide. It's got OH minus right there. All right. Last one is sodium chlorate. That is neither an acid nor a base according to Arrhenius. Okay. So that's your number 7. All right. Make sure you know the Arrhenius definition of an acid or base. You can go through something like that fairly easily, just looking for H's in front. And hydroxides, being careful about things like water and any kind of salt or ionic compound other than hydroxide is going to be neither. Number 8. Number 8, write down the formula and label, and you could write down pretty much anything for this, okay? So I'm just going to go ahead and write down a few. Monoprotic, all right, let's just say HBr. That's a good monoprotic acid. A diprotic acid, H2SO4. All right, a triprotic acid, there's actually not a whole lot of them. Citric acid is a triprotic acid, and phosphoric acid, H3PO4. Very simply, monoprotic, diprotic, triprotic. Okay, you guys should be able to do that. Just an example. Yeah, that's good. All right, and I might ask something like this, or I might just have a which of the following is diprotic, and you just pick out the H2 one. So number 7 and 8 should be easy. Number 8 maybe being the easiest of all. Okay, question. We had no idea what that meant. Really? You had no idea what 8 meant? Well, we've had a problem like this before on the first homework one. So anyway, yeah, that's what I meant for number 8. So we should just look up examples on the internet, or should we have it memorized? Well, no. When I'm probably not going to ask a question with that wording. I'll probably say, which of the following is diprotic? Or which of the following is polyprotic? Or which of the following is monoprotic? And you just circle the thing. You'd be like, you count the H's and you circle the thing. Okay? So that's the difference between a test question and a review question. Okay? Hopefully that makes sense. Yeah, I know. It's lovely when it gets a little awkward like that. All right, number 9. Starting to get a little bit harder. Bronsted-Lowry. All right, label the acid base and the conjugate acids and conjugate bases. So we are we should be really good at conjugate acids and bases by now, after the whole review that we've done with the buffers. But let's do this now. So when you see this, the first one's pretty straightforward. Actually, I should have made a harder one on here. I should have made one with two different acids. These are pretty straightforward, but let's just go ahead and do this. So maybe I'll make up another one that's a little bit harder, because you might see another one. Okay, but anyway, so this one clearly is the acid. This one's clearly is the base. Why? Because this one cannot possibly be an acid because it has no H's in it, which means by default this one has to be the acid. Okay, and so let's just check and follow along. using the method that you might have to if both of them could possibly be an acid. So you have H3PO4 over here, and you follow the PO4. You find the PO4 over here and see, okay, when it's going from here to here, what's it doing? It's going H3 to H2, which means it's losing an H. So that means that this is the acid, and this is the conjugate base, okay? Which means the other one must be acting as the base, and let's verify. It's going from CO3, so NaCO3, to NaHCO3. And this is actually, I must have made a typo. NaCO3 is not a thing. It should be Na2CO3, which means, yeah, that's the only mistake there. That should be Na2CO3 because carbonate's CO3 2 minus. So sorry about that. So this is a base and is getting an H over here. So this should be the conjugate acid. All right. Same thing here. All right. So we have H2SO4 and NH3. So H2SO4, we find the SO4. You always follow the anion part of it. So you follow the SO4 over here. Here it's got 2 H's. Here it's got none. So this is going to be the acid, and this is going to be the conjugate base. Now keep in mind that this is actually the conjugate base of the conjugate base, but we can just label it as conjugate base here, okay, for this reaction. And we look at NH3, NH4 plus, so this thing is gaining an H. It's going from 3 H's to 4 H's, so this must be the base. The base is the one that accepts an H and turns into a conjugate acid. All right. So poly just means, poly doesn't mean anything more than 3, actually. So poly protic up here basically means not monoprotic. Poly means more than one, okay? So in general, diprotic, triprotic are all examples of polyprotic. I know poly means many, and so you'd think that would mean like more than 3. That would make sense, but actually polyprotic just means more than one. It means it's not monoprotic, okay? All right. Yeah. Let me make up another example for this one. I just want to make sure that we're really getting that. So number 9, all right? Because I should have made up a harder problem. Let's do something like this. So let's say you have HClO4 plus HClO3. This is going to be tricky. All right, these are going to look really, really similar, and you'd be like, "What's up?" And so to do this, they're going to react, and it's going to make ClO4 minus plus H2ClO3 plus. All right. So when you see a problem like this, where you have 2 things with H in front, 2 acids, and you have 2 things over here, you can't just look and say, okay, all right, that one's the acid, oh, and that one's the acid. So you have 2 things that are Arrhenius acids. Well, which one is going to be the Bronsted-Lowry acid in this reaction? And so let's check it out. So you have HClO4 turning into, well, follow the ClO4. Okay, so you have ClO4 over here. So this one is the one that is losing the H. It's going from HClO4 to ClO4 minus, which means this one is the one losing the H. So this is the acid. And this one is going to be the conjugate base. Okay, which means the other one must be the base, but let's verify. You've got HClO3 going to H2ClO3 plus, so that one must be the one that's acting as the base. It's gaining an H. And so this is going to be your base, and this is going to be your conjugate acid. All right, so be prepared for that too. All right, so how do we know that it makes that? You don't worry about that. I'm the one that knows this reaction. You don't need to predict any kind of reaction like that. That would be insane for me to ask you to solve a problem like that and say, okay, what's it going to make? I know what it makes. You just need to identify the acid and the base, the conjugate acid, the conjugate base. Okay. Like, can you explain how we come up with, yeah, like I said, you're not going to come up with that. Okay? I give you everything in blue. You write the red and the green here. You identify the acid, the base, conjugate acid, the conjugate base. Okay? Yeah, figuring out the products of those are pretty hard. Yes, figuring out the products of those are hard because you don't know the relative reactivity, the relative acidity of these things. Again, don't worry about that. Okay? Yeah, sorry, same question. So, but you do need to do, let's see, something like this. This is a more straightforward kind of neutralization reaction, okay? This is the only kind of situation for an acid-base reaction where I'm going to say that you have to actually write out the reaction, all right? And so let's go ahead and just do that because you're asking, and then we'll go through the other ones, all right? And so I need to go ahead and I'm going to solve all the rest of these, and then I'll take any questions. But because of time purposes, I have to just go ahead and solve these, okay, guys? So, balance reaction of this. When you have an acid and a base, so you're going to have a pretty straightforward, so something like this with a base with an OH minus. That's going to be your kind of neutralization reaction that you have to write out. It's not going to be anything crazy, okay? So what do? You take the OHs and you turn the H's into water. So H plus and OH minus, and it's going to be the basic is going to be H plus OH minus goes to H2O. And then you have to combine everything else together. So this is the general neutralization reaction right there. And then you have to deal with all the different specifics of this problem. Now you have 2 moles of this and 2 moles of that, which is the same as 1 and 1. So don't expect that necessarily these numbers in front are going to be the numbers in the balanced reaction. So you have a 1-to-1 ratio, okay? 2 to 2 is the same as 1 to 1. So let's write out the reaction. So we have H3PO4 plus LiOH. I'm going to have H plus and OH minus is going to go to H2O. Now, because you have 1-to-1, that means although you have a triprotic acid, you only have 1 hydroxide that you can use to neutralize that. Okay? And so therefore, only 1 H is going to be neutralized. That's important, which means you're making water, so it's going to be 1 to 1 to 1. And then what's the other product? Well, this is left as lithium, and this, only 1 H is being removed because you have only 1 hydroxide to remove it, so it's going to be lithium H2PO4. All right, so this is the answer to number 13, okay? That's the answer. And any kind of neutralization reaction that I give you on the test will be an H plus OH minus makes water. It will make water. It'll be making water and something else, and that something else is, you're going to have to figure out what in the world that is. Okay? And the amounts matter. So the amounts will tell you, am I doing 1 neutralization or 2 or something like that. So back up here. I did have a question earlier about Lewis acids, Lewis bases. I really just want you guys to be able to do one problem that's like this. Which one's the acid, which one's the base, and how do you know? Okay? So simply put, the acid is going to be the one that wants electrons, and the base is going to be the one that has extra electrons. So PCl3 and BCl3, if you go through the Lewis diagrams, or even if you look on the periodic table, boron has only 3 valence electrons, where phosphorus has 5. So phosphorus has an extra 2 valence electrons. So right away, you're thinking phosphorus has extra electrons and boron doesn't have enough. So boron's going to be the acid and phosphorus is going to be the base. And that, in fact, is the case here. Okay? So if you look at the Lewis diagrams, your BCl3 is going to be something like this, where the boron doesn't have an octet. It wants an octet. But the phosphorus is going to look exactly the same, the PCl3, except one difference. It has 2 more electrons than boron. And because it has 2 more electrons than boron, right there, it's going to act as your base, your Lewis base, and your boron, which doesn't have those, is going to act as your acid. And what can happen is that these electrons can form a bond with boron, and the boron and the phosphorus can share those electrons, okay? In a kind of a Lewis acid, Lewis base way that you can form a bond between boron and phosphorus because phosphorus has an extra lone pair. And you might be saying, okay, what about all the chlorines? Yeah, the chlorines do have extra electrons, but the chlorines really, really want them, and so they're not going to really share. Okay, so we're not going to worry about those. All right. It should be something fairly obvious like this. Boron or aluminum, typically you're going to see boron or aluminum are going to be your Lewis acid. All right, and it's going to be whatever, something like that. All right, they're very, very common. Now there's other ones like antimony and all that kind of stuff, but we're not going to get into those kinds of crazy Lewis acids. Number 11, down here. Number 11, fairly straightforward. Okay, first of all, you need to identify, is that an acid or is that a base? And that's going to be, so HCl, that's an acid, so it's going to be negative log of 9. So that gets us a pH of negative 0.95. All right. Here we have, once again, we have an acid, H in front, that's perchloric acid. So this is going to be a negative log of 0.0044. That's going to be 2.36. And then rubidium hydroxide is a base, so you're going to use 14 plus the log of 0.00075. All right, and that's going to be a pH of 10.88, rounding up. Okay? So notice that all of these, I'm giving 2 significant figures. Significant figures are all the numbers that are after the decimal point, right? 2 sig figs, 2 sig figs, 2 sig figs. Okay? How many times more acidic is a pH of 3 than a pH of 6? Okay? It's going to be 10 to the 6 minus 3, which is 10 to the 3rd, which is 1,000 times. How's another way that you can think about that? pH of 5 is 10 times more acidic. pH of 4 is 100 times more acidic. But pH of 3 is 1,000 times more acidic. Each step is 10 times an increase in acidity. Each pH of 1 is 10 times more acidic. Okay? Now, I think, all right, so we're gonna kind of run out of time here, and I do have a class after this. So let me just go. Which one do you guys want me to do? I'll go over 14 or 15, and then what I'm going to do is I'm going to just send you guys a picture of my answers because I have a class here in a little bit, so I can't stay longer on this particular live stream. What is 2 over 2? So it's therefore everything would be 1. Yeah, yeah. And P was negative needed to be the donor to go to 0. For Lewis acid, Lewis base, you're just looking for, is there a lone pair on that central atom or not? And you find, specifically, you find something that's, let's say, a non-octet thing like boron or aluminum, which would be non-octet, and then they're going to be the Lewis acid. So that's really what you're looking for. You're looking for, okay, which one wants electrons, which one can give electrons. All right, acid base. Okay, it's 13.2 moles. Which one's 13.2 moles? Number 15. All right. You know what? I'm going to run out of time. Are there any? Yeah, please. I'm going to run out of time. So what's going to happen is I'm going to close up. I'm going to solve these problems. I'm going to send it to all you guys. I'm going to send you guys my answers. You guys can look over it, check your answers. I got 1 more minute here. Do you guys have any questions at all? Yeah, so in 13 is 2 moles. Yeah, so number 13, we have 2 moles and 2 moles is the same as a 1-to-1 ratio, if that's your question. And so, you know, you can do that. If it's 0.5 and 0.5, then it's the same as 1 and 1. What matters is the ratio, whole number ratio. So if you had 2 and 4, that'd be the same as 1 and 2. Okay? Okay. Any other questions? Please check the chat. Sam, any other questions? I'm checking the chat. I don't see anything else. Yeah, you said B was the acid because its charge was +3. It doesn't really have a +3 charge here, right? It just, when it's in a compound, it's neutral. They're both neutral. So you can't just look at the charge, right? So you have to look at which thing wants electrons, which thing can give electrons. So that's the real key to this Lewis acid-Lewis base pair, okay? And there's, unfortunately, there's not a whole lot of options of what I can give you. So typically, honestly, your boron and your aluminum are going to be your Lewis acids and Lewis bases. But there are some other things that I could give you, but they get to be crazy looking. Okay? All right. So let me see. Any other? Yeah, estoy. All right. Sorry about that. All right. I'm just going to close out here, and I'm going to solve these for you guys. I'm going to post them here later this morning. I'm just going to take a picture of my answers, and that's it. Because I do have another class I have to get to right now. If you guys have any more questions, you can send me an email what your specific question is, and I'll try to answer it via email, or you could post it on Google Classroom or something like that. For number 5, we add any compound or not? Number 5. Number 5. Well, not anyone, but yes, as long as you're doing these things, okay? So for number 5, which I'm assuming is this number 5, you have to add, you can't just add any acid, you have to have add the conjugate acid, or when you partially neutralize it, it has to be a smaller amount of a strong acid, even with the 1-to-1 ratio. All right, partially neutralizing it is going to be not a 1-to-1 ratio, and then this doesn't have to be a 1-to-1 ratio. It can be any ratio. Okay. No, I mean the second one. Bummer. The second one here, yeah, it could be any strong acid, which typically but you have to be careful if you use like polyprotic acids. You want to use probably a monoprotic acid just so you're careful. Okay. All right. So yes, this doesn't have to be HCl, but it should be HCl, or it could be HNO3, or it can be HClO4. It has to be some kind of strong acid. It should be a monoprotic acid, so you don't get all confused about the ratios there. It gets really confusing if you use something like H2SO4, which you don't want to use, okay? All right. Can't you make more water? All right. I'm going to have to go ahead and sign out here. So I'd love to sit and chat, but I got another class. So blessings, guys. Go to your Spanish class or whatever else that you got right now. See you guys.